Now let's talk about the direction of your hypothesis. You remember that this is our null hypothesis, which is consists of two things: its expected value and direction. So we didn't discuss direction much, so let's talk about the direction. Well, first of all, if you think about the direction, then you have actually three different possibilities, right? So these are all possibilities where you have the same value but different directions. So this is the hypothesis we already considered several times, which is mu for population is equal to 10 or greater. In this case, the alternative hypothesis is that mu is less than 10. So the direction is opposite. So this is opposite to this one, right? So you have the direction of the null hypothesis and direction of alternative hypothesis. This is another hypothesis. Here we assume that the sugar content in population, average sugar content in population, does not exceed 10. So in this case, the value is the same, but the direction is less. And in this case, the alternative hypothesis will have the opposite direction, greater, right? Finally, you can assume that the population has exactly 10. No more, no less. In this case, you don't have any direction, neither in null hypothesis nor in the alternative hypothesis. So the value is the same in all these three cases, but the direction is different. Let's take every case and consider using some example. Okay, I will use the same case study, 5 apples taken from the same population, and then all the calculations the same as I used before. So the average is 9.5, standard deviation 0.45, and standard error is 0.20. Now let's start with the hypothesis that we already know. It's the 10 or greater, and let's talk about this one. Remember, this is the way we compute a t-score, and t-score doesn't depend on the direction. It depends only on the value of your null hypothesis, and therefore you will find out that the t-score will be the same in all these cases. So what will be the difference? The difference is the way how we compute the probability, because the difference is the way how we treat if sample is extreme or not extreme. You remember that this direction, it's a direction for the less extreme samples, right? And this direction, it's a direction for more extreme samples, right? And how we define it? We remember that greater is on the right side and less is on the left side. So this is the situation that we have. So this is exactly the average of our sample, and this is the t-score for our sample for given value of the null hypothesis. And therefore, the right side, it's the greater, right? It's the direction for the null hypothesis. It's a direction for the samples which are less extreme. So these are the even better samples for the null hypothesis. They fit even better for this assumption. But the right side, it's this less. It's a direction for alternative hypothesis. And this is exactly what the more extreme samples are. So when we use this hypothesis, and when alternative hypothesis is less, we should use the left side in order to compute the p-value. So that's what we call a left tail test. So left tail test because we use a left tail for the t-score to compute the p-value. Okay. So in this case, we know that the p-value will be 0.033, and that's exactly the p-value for this null hypothesis, for the left tail hypothesis. So when you have a null hypothesis like this, mu is equal to a particular value or greater, then the alternative hypothesis will be mu is less than this particular value. And this one defines the direction of the test, and it's a less, it means it's a left tail. So therefore, this is a left tail test. Okay. Now let's consider the second one. So in the second one, you can see that the hypothesis is that 10 or less. Because we didn't change the value, we didn't change this 10, the t-score will be the same, minus 2.5. But now the way we treat the extremeness is different, because now we expect 10 or smaller, right? So it means that all values which are even smaller are good for our sample. So all these samples which have t-score below 2.5, minus 2.5, or the average below 9.5 grams will fit very well our null hypothesis, right? So they will be even better, even more convenient for the null hypothesis that we have compared to our sample. So it means that the other tail, the right tail, that's the direction of the alternative hypothesis, greater, That's all the samples that are extreme, more extreme than we have, more extreme than we have. So this is the direction of the extreme samples, right? And that's exactly how we compute a p-value in this case. So we use right tail because it's exactly the direction of the extremeness, it's the direction of the alternative hypothesis. And in this case, apparently the tail will be the right tail test. So if you compute the probability, you remember if this is 0.033, so apparently in this case it will be 1 minus this, so it will be 0.967. You can see the p-value is very large, so it supports the null hypothesis really, really well. So it means that our sample is not extreme for the null hypothesis that we have. Our sample supports this null hypothesis in this case, right? So if your null hypothesis looks like this, particular value or less, then the alternative hypothesis will be larger or greater than particular value. So greater, it's the right side. And therefore, the tail that you should use for computing the probability, for computing the p-value, it's called, it will be the right tail, and therefore the test also is called right tail test. So finally, the last case. In this case, we don't have any direction. But what does it mean? If we assume that mu is exactly 10, then both directions are extreme. So it means that if your sample is 9.5, if your sample average is 9.5, it's 0.5 grams smaller than your population assuming average, right? But it means that in other direction, you have sample which is equally likely extreme. It's this one. Because this is smaller, right? It will be 0.5 grams larger. Because we assume that it's exactly here. So both directions are the directions of extremeness. Are the direction of extremeness, right? So in this case, the sample which are equally distanced from the population assuming population average, but in the other direction will be as extreme as the sample you have, and therefore any samples in between will be less extreme. So this is the area where you have the samples which are closer to 10, which are closer to expected values, and therefore they are less extreme than the one that you have. Now you see how to compute probability to get a sample that are more extreme. We should take these two areas. So these are more extreme in one direction, these are more extreme in the second direction. Okay. So that's the way to do that. We know that this probability is 0.033. Apparently, because t distribution is symmetric, this probability will also be 0.033, and your p-value will be a sum of these two probabilities. So it will be 0.066. And because we use two tails, we use both tails to compute the p-value, the test will also be called two-tail test. So we have either left tail test, right tail test, or two-tail test, and which tails to use, it depends on the direction of your null hypothesis. Okay. Now I recommend you to go to Grasta again and play with this app, one sample t-test, where you also have the left tail, right tail, and both tail hypothesis. So play as much as you can, and the next video tells you how to use this app. So watch this next video first, it's very short, and then play with this app and come back for the next step.